Welcome back to the Machine Learning 101 course. Today we will cover a very important topic, deep learning. We'll start with a quick recap. Neural networks are an interconnected network of neurons that are organized into input, hidden, and output layers. It's a very flexible architecture and the foundation of deep learning. Fully connected neural networks, also known as ANNs, pose certain limitations when used for image classification tasks. CNNs address this problem by using convolution and pooling layers. Convolution layers scan the input image using learnable 2D or 3D filters to detect and capture spatial patterns in the image. In a typical CNN architecture, there are multiple convolution layers. Initial convolution layers recognize simple features like edges and loops, and as information passes through more layers, the subsequent convolution layers assemble these features to learn more complex features. With CNNs, we've already gotten a taste of deep learning. Now, let's understand it further in this video.
Well, deep learning is part of machine learning. It's, again, in itself, a group of techniques that are in machine learning. So when you say machine learning, you are actually including deep learning inside the picture. But when we want to compare machine learning and deep learning, of course, what we're trying to compare is the traditional machine learning algorithms with the deep learning algorithms that have been improved in the last decade. All right, so let's look into how they're different. Traditional machine learning algorithms on one side and deep learning on the other side. So the first and most prominent difference is that when you are training machine learning algorithms, you need features extracted from the data manually. And when you're doing deep learning training, you don't have to do that. So just to give you an example, let's say you're trying to classify cats or dogs, the most common example on the internet. So what happens is when you want to train your model to understand if a given picture is of a cat or a dog, you have to extract features such as how many pointy ears it has, what does the nose look like, what is the color of the nose, what is the pose that the animal is giving, for example. This is just an abstract example of what kind of features that you can extract. Whereas for deep learning, you can just give the image as it is to your deep learning algorithm, and it will itself understand what the pattern is and what the features are that are separating the two animals from each other in these photos. And this is very nice, right? Because when you're training deep learning models, you do not have to do feature engineering at all. But of course, this nice little feature comes with a cost. When you're training deep learning algorithms, you have to have much more data than you need for traditional machine learning algorithms to be able to train your model to be accurate. And also, due to all the computation that needs to be done in deep learning algorithms, you have to have a stronger machine, which has higher processing power, and it's going to take a longer time. But that's kind of like a trade-off, of course. The stronger the machine that you have, the less time it's going to take. But on average, it's always going to take longer to train deep learning algorithms that compared to the traditional machine learning algorithms.
A very powerful and important concept for deep learning is embeddings. As we learned in the last lesson, the sequence of convolution plus pooling layers act as feature extractors, and the final output is flattened and fed into a fully connected neural network to make the prediction. In this example, when we flattened the output of the last pooling layer, we effectively converted our input image that was represented as a collection of RGB pixel values to a smaller and more dense feature vector of, let's say, a size 100. This feature vector is the input image's embeddings in a 100-dimensional semantic space. It is like the image's semantic signature. The important characteristic of the semantic space is that two images that are very similar to each other will have embedding vectors that are pretty close to each other. And this concept of embeddings can be extended to any input. Another very common application is text, where we create words or sentence embeddings. Earlier, we had used a bag of words approach to vectorize variable length sequence of terms to fixed length numerical vectors. We can also use word or phrase embedding vectors to train a sentiment classifier or for other natural language processing tasks. But, as you can imagine, these approaches have limitations because they depend only on the presence of a term or phrase. They do not preserve the order of tokens and do not do well for applications that depend on the context, like autocomplete. Just like CNN architecture helps with spatial context for images, RNNs help preserve the context for text inputs.
Consider the standard neural network. We have an input X going into some hidden layer H. The output of the hidden layer is passed to an output layer, which has some activation function to produce an output Y hat. We'd like to process the sentence, "The dog looked guilty," as a sequence where each word is represented by a word embedding. So to start, we pass the encoding for the word "the" into the neural network. Now what? If we just pass in the encoding for the word "dog," it'll be as if the neural network is looking at a new independent input, and there will be no connection to the previous word. There is no memory, so to speak. We need a way to link the word "dog" as part of the same input. The approach here is to add a recurrent connection where we feed the output of the hidden layer back into the hidden layer itself for the next word in the sequence. The hidden layer then receives two inputs: the current input X, so the embedding for the word "dog," and the output of the hidden layer for the previous word, "the." More formally, we say it receives the hidden layer output from the previous time step. To clarify this, we can add subscripts. So X sub t, H sub t, and Y hat sub t are part of the current time step. And the recurrent connection feeds H sub t minus 1, the hidden layer output from the previous time step, into the current time step. This forms a simple recurrent neural network, or RNN. An RNN is less an architecture and more of a concept. As we'll see, there are different architectures which use recurrence. This is a view of an RNN unrolled over time, so it's the same RNN at different time steps, so we can more easily visualize what's happening. So to process the sentence, the encoding for the word "the" goes into the network at T1, and the corresponding Y hat is generated. At T2, the network takes the encoding for the word "dog" and the hidden layer output from the previous time step, carrying information about the word "the." These are combined to produce an output for the second time step. The critical thing here is that Y hat at T2 is based on the sequence "the dog," and in this way, information about the sentence is carried forward through the network over time. At T3, same thing. Y hat at T3 is based on the entire sequence up to that point, which is "the dog looked." And finally, at T4, the last Y hat output, it takes the entire sequence into account. So at each time step, the network creates a representation of the sequence up to that point, and through this recurrent mechanism, the network has some sense of memory.
Now that we understand RNNs, let's look at what a language model is and how RNNs are used to generate text.
We can now also learn about language models. Consider this sentence: "She spent the day swimming in the blank." What's your guess? Lake? Reasonable. Ocean? Sure. Milkshake? Bleach? Probably not. We know that, given a sequence of words, the probability of certain words occurring next is higher than others. Language is predictable. A language is governed by rules and also our shared understanding of the world. And anything governed by rules is predictable. Put another way, some sequences are more probable than others. And that's what a language model quantifies. A language model determines the probability of a sequence of words. So from our previous example, the word lake following a particular sequence of words may be 0.6, I just made that up, whereas the word milkshake following the same sequence may be 0.02. More formally, the probability of a certain sequence is the product of the individual probabilities. So the probability of the first word occurring times the probability of the second word occurring given the first word occurred, and so on. Language models are foundational in NLP. They're used in speech recognition, translation, autocorrect and autocompletion, and text generation, which of course is required for everything from summarization to question answering to dialogue systems. You may have heard of or played with the famous GPT models. Those are language models. If you're watching this video, language models are part of your everyday life. And RNNs will provide our first foray into language models, as we'll see in the demo. Let's look at how we would train an RNN-based language model. Much like Word2Vec, training is self-supervised. We start with the corpus and segment it into pieces, whether it's fixed-size chunks, sentences, paragraphs, or documents. Each piece is now one training example. The longer each piece, the more expensive the training, because the RNN has to process and backpropagate across more time steps. For this module, assume we segment our corpus into sentences. Let's say this is a fragment of one of the training examples. We have a word embedding for each word. Training begins by feeding the first word embedding into the RNN. This is the first time step, so the previous hidden state at this point is a zero vector. The embedding goes through the hidden layer, and a softmax in the output layer creates a probability distribution over the entire vocabulary. Y hat then is each word's probability of being next in the sequence given what the network has seen so far. In this case, the word she. Now, we want to train the RNN to assign a higher probability to the next word based on the training data. In this case, the expected next word is swam. So what we can do is use the next word in the training example as a target for the current time step. So now we have a target Y, which, as we've seen, can be a one-hot encoded vector or an index for the correct word, and a Y hat, which is a probability distribution. If you recall from Neural Network Foundations 1, when we have a situation like that, The categorical cross-entropy loss is just the negative log probability of whichever y hat value corresponds to the target. In other words, the loss for the current time step is just the negative log probability of the word swam. And of course, the higher the y hat probability for swam, the lower this loss is going to be. And that concludes one time step. In the next time step, the next word in the training example, swam, is fed into the RNN along with the previous time step's hidden output, and a loss is calculated. In this case, the loss is the negative log probability of the word in from y hat. And this continues until we process the whole example, or more commonly, a batch of examples. At that point, we can calculate the overall loss and use backpropagation through time to adjust the weights to further minimize the loss. So at the beginning, the network will be guessing the next words in the sequence randomly, but over iterations should get closer and closer to mimicking the training examples. Note how at each time step, we're feeding the correct next word into the RNN. In this example, at time step 3, the word in is fed to the RNN. By doing this, we're giving the RNN a more focused classification task. In this case, the inputs are the embedding for the word in and the hidden state vector representing she swam. The output is a probability distribution for each word in the vocabulary being next in the sequence. And once we have the output, we calculate a loss and ignore the output itself, and instead feed the network the next correct word in the sequence. This technique is called teacher forcing, and we'll see this in the demo. Once our RNN is trained, generating text is straightforward. It begins with feeding the RNN an initial token. This can be a special start token if you want the RNN to generate the entire sentence from scratch, or we can also feed a particular word token to prime the network. From there, the output layer has a softmax to generate y hat for this time step, which will be a probability distribution over the vocabulary. To determine the next word, this probability distribution is sampled. So the word that's picked doesn't have to be the one with the highest probability, but a word that's likely. And that's a simple way to inject some variety into the generated text. In this case, let's say it's the word the which ends up getting picked, which is reasonable to expect as the beginning of a sentence. From there, the RNN cell at the next time step takes the value of the hidden output from the previous time step, and it also needs to take in a new X input. The X input in this case will be the sampled word from the previous time step, the word the. And once again, the output layer softmax creates another probability distribution over the vocabulary which gets sampled. And let's say the word cat gets sampled during this time step. And it goes on like this from there. Each new word is generated by sampling from a probability distribution that's based on the sequence up to that point. And it continues like this until a certain limit is reached or a special end token is outputted.
At its core, ChatGPT is nothing but a very large language model.
The heart of ChatGPT is an LLM, or a large language model. The default LLM for ChatGPT is GPT 3.5. ChatGPT could also use the latest GPT-4 model, but there is not much technical details on GPT-4 yet for us to talk about. Now, what is large language model? Now, a large language model is a type of neural network-based model that is trained on massive amounts of text data to understand and generate human languages. Now, the model uses the training data to learn the statistical patterns and relationships between words in the language, and then utilizes this knowledge to predict the subsequent words, one word at a time. Now, an LLM is often characterized by its size and the number of parameters it contains. The largest model of GPT 3.5 has 175 billion parameters spread across 96 layers in the neural network, making it one of the largest deep learning models ever created. The input and output to the model are organized by token. Now, tokens are numerical representations of words, or more accurately, parts of the words. Numbers are used for tokens rather than words because they can be processed more efficiently. Now, GPT 3.5 was trained on a large chunk of internet data. The source data contains 500 billion tokens. Looking at it another way, the model was trained on hundreds of billions of words. Now, the model was trained to predict the next token given a sequence of input tokens. It is able to generate text that is structured in a way that is grammatically correct and semantically similar to the internet data it was trained on. Now, but without proper guidance, the model can also generate outputs that are untruthful, toxic, or reflect harmful sentiments. Even with that severe downside, the model itself is already useful, but only in a very structured way. It can be taught to perform natural language tasks using carefully engineered text instructions, or prompts. This is where the new field prompt engineering came from. Now, to make the model safer and to be capable of question and answer in the style of a chatbot, the model is further fine-tuned to become a version that was used in ChatGPT. Fine-tuning is a process that turns the model that does not quite align with human values into a fine-tuned model that ChatGPT could use. This process is called reinforcement training from human feedback, or LLHF.
In this week's hands-on exercise, we will do something slightly illegal. We will learn how to give ChatGPT an assessment task sheet and get it to generate a report for us. You will need to get an OpenAI API key, which you can do using the link in the description below. For this week, I strongly recommend you experiment more with the OpenAI API key. Hence, there is no specific task to be completed. You can try using ChatGPT for some other purpose in your code, or try out new models altogether, like DALL-E. To learn more about model memories and natural language processing, check out these videos. So far, we have discussed classification and regression problems, both of which are supervised learning. But there are many more interesting and important problems beyond supervised learning where machine learning can be of great benefit. We will learn about these in the next video, which will be the final video for this course.